Welcome to the Deep Dive, the place where we cut through the noise to understand the foundational figures who shaped our modern world. And sometimes those figures are, well, strangely missing from the popular history books. Today, we are shining a very bright spotlight on one of the most powerful yet uh, understated gravitational forces in 20th century physics, Arnold Sommerfeld.
Understated is the perfect word for him. We're talking about a man who is absolutely central to the transition from classical mechanics to quantum reality.
He was the vital bridge builder, the indispensable mathematical engine. And yet, outside of physics departments, his name just doesn't carry the same weight as his contemporaries.
Not at all. Not like Einstein or Bohr. He's this great paradox of modern science.
He really is, and it's a profound historical and, I think, scientific irony. The sources we've gathered for this just highlight that paradox over and over again.
They really do. I mean, consider this one fact. Sommerfeld holds the undisputed record for having mentored the highest number of eventual Nobel laureates.
We're talking about the giants, right? Werner Heisenberg, Wolfgang Pauli.
Bethe, the list goes on. These were his students. But then you look at him. He himself was nominated for the Nobel Prize an astonishing 81 times.
81 times. That's just, it's not a snub. That's something else entirely.
It's a pattern. It suggests a deep, maybe even a systemic misunderstanding of what his actual role was in that whole scientific ecosystem.
So our mission for you, the listener, is to unpack that paradox. We want to go beyond the Nobel stats to really understand Sommerfeld's dual genius. First, as this theoretical pioneer who took revolutionary, sometimes kind of crude ideas and gave them the mathematical rigor to actually work.
And second, as this foundational educator who created a unique school, a culture really, that shaped the very physicists who delivered the modern quantum revolution.
Exactly. We're tracking a life that spanned from the late 19th century all the way through 1951. He had to navigate the most turbulent, the most creatively destructive era physics has ever seen.
And he wasn't just adaptable. He was a master synthesizer. He moved so seamlessly from applied math and electromagnetism through his pivotal work on the quantum atom, introducing the fine structure constant, all the way to laying the groundwork for modern solid-state physics with his free electron model.
And that's the core question, isn't it? How did his early, really grounded work in engineering give him the toolkit to handle the purely abstract, bizarre world of the quantum?
Okay, so let's unpack that starting point. When you look at Sommerfeld's early career, what's immediately striking is his intellectual DNA. He wasn't trained as a purely abstract mathematician, was he? He was steeped in applied mathematics from the very beginning.
Absolutely. He was actively bridging pure theory and practical real-world engineering problems right from the get-go. And the cornerstone of that training came straight out of the University of Göttingen.
Which was the center of the mathematical universe at the time. It really was. And specifically, his association with the mathematical giant, Felix Klein. Klein was this huge advocate for applied math. He believed it should serve technological progress, and he deeply, deeply influenced Sommerfeld's whole approach to problems.
So he pushed for rigor, but always with an eye on the application.
Always. And crucially, Klein also influenced Sommerfeld's art of lecturing. He taught him how to turn math from this dry recitation into a compelling narrative. That's a skill Sommerfeld would later perfect in Munich.
And their collaboration, it wasn't just a casual mentorship, was it? This was a defining intellectual effort.
Oh, it's a 13-year marathon from 1897 to 1910. And it resulted in this massive 4-volume text, Die Theorie des Kreisels, the theory of the gyroscope.
The theory of the gyroscope, that sounds incredibly specialized.
It is, but the sources really emphasize its breadth. It was specialized, but deliberately broad in its application. I mean, think about it. The gyroscope was the perfect laboratory for high-level applied mathematics at the turn of the century.
Right, because it involves rotation, stability, all these complex dynamics.
Exactly. And the structure of the book shows this. The first 2 volumes were purely about the mathematical theory of rotation and stability. Very abstract stuff. But the last 2 volumes, they were entirely dedicated to applications in diverse real-world fields.
Like what, for example?
Geophysics, astronomy, like calculating the precession of the equinoxes, and most importantly, industrial technology.
So studying the gyroscope wasn't just some academic exercise. It was training in complex dynamical systems.
It was training in how to synthesize pure math with messy physical constraints, like friction or variable external forces. You had to make the theory work.
It forced him to develop this sophisticated mathematical apparatus that was adaptable to non-idealized systems.
Precisely. And that intellectual flexibility, that need to make high theory work on a vibrating bridge or a spinning planet, That's the core trait Sommerfeld carried with him into the quantum era.
And this applied focus, it led directly to a critical career pivot for him.
It did. In 1900, he's appointed professor of applied mechanics at the Technische Hochschule Aachen, which is now RWTH Aachen University.
A dedicated engineering school, that's a huge shift from pure academia.
A crucial move, and it was orchestrated by Klein, who saw that Sommerfeld's skill set was perfect for modern engineering education. His role was explicit. Teach future engineers how classical disciplines like strength of materials or dynamics could be built on a consistent, high-level mathematical foundation.
So this required him to get his hands dirty to engage with industry problems.
Deeply. The sources give us some really vivid details here. This was hands-on collaboration with practical engineers.
So what kind of engineering problems was the future quantum theorist tackling?
Well, for instance, he worked with a guy named August Fuppel on complex problems involving resonance in the vibration of bridges.
So understanding why things shake apart, that requires incredibly precise analysis.
Immensely precise. He consulted with Otto Schlick on similar vibration phenomena in ship stability, roll, that kind of thing. And maybe most relevant to industry, he worked with August von Borries on locomotive construction, optimizing the dynamics and structural integrity.
These are not abstract problems. You can't fudge the numbers on bridge resonance. The bridge collapses.
Exactly. This period ensured he was accepted as a useful member of engineering practice. He was providing expert mathematical opinions to the Ingenieurverein, the engineering association.
The mathematical precision you need to model the nonlinear dynamics of a steam locomotive. I mean, that must have prepared him for the messy equations of the quantum atom years later.
It's the same mindset. It's about taming complexity with rigorous math.
And it was during his time at Aachen that he started developing theories that would have massive implications down the line, especially in fluid dynamics.
Yes, he established this deep expertise in the theory of hydrodynamics, a subject that would interest him for decades. And this wasn't just abstract wave theory. When he moved to Munich, two of his most brilliant and diverse students, Ludwig Hoff and, pretty surprisingly, Werner Heisenberg, would write their PhD theses on this very subject.
Heisenberg wrote his thesis on fluid dynamics.
Specifically on the theory of turbulence and stability. It just goes to show you that the core of the Sommerfeld school was rooted in classical mechanics.
That's a powerful testament to his teaching. And then there's this surprising connection to tribology, the science of friction.
The field of tribology still sees him as a founder. His work on journal bearing lubrication was absolutely fundamental.
Journal bearings, those are critical components in engines, turbines, anything that spins.
Exactly. And understanding the hydrodynamic forces in there required a super sophisticated mathematical model of fluid flow under pressure. His contributions were so crucial that he was named one of the 23 men of tribology. It's the Sommerfeld style in a nutshell. A deep theoretical investigation, demanding powerful math, but stemming directly from an industrial problem.
So we have this picture of a mathematical mind steeped in empirical truth and industrial applicability.
And this all fed into his ultimate textbook legacy in classical physics.
Right, the multi-volume lectures on theoretical physics.
A masterpiece of education. Volume 1 on mechanics and Volume 6 on partial differential equations are still praised. They're noted for their incredible clarity, the thoroughness of the derivations, and their ability to connect theory to physical insight.
And his classical mechanics text from the 1920s is ranked right up there with the major works.
It really is. It's deservedly ranked alongside Whittaker and the later highly respected Landau and Lifshitz series. It just showcases the pedagogical rigor he inherited from Klein and perfected at Aachen. Now, if we connect this foundational expertise, this commitment to rigor and applied math, to the broader philosophical landscape of physics in the early 1900s, that's where the revolutionary tension really starts. See, Sommerfeld wasn't just a general classicist. He was initially a staunch defender of classical electromagnetism.
And that put him in direct philosophical conflict with the radical quantum ideas coming from Planck and Einstein. Here's where it gets really interesting. It's so hard to imagine the architect of the atomic fine structure starting out as a skeptic of the quantum revolution itself.
But he was. He was dedicated to what the sources call the electromagnetic worldview.
Okay, so what did that actually entail for a top-tier physicist like Sommerfeld?
Well, it was essentially a post-mechanical paradigm. A lot of physicists of his generation had seen the old mechanical worldview, trying to explain everything with tiny hard spheres and gears. They'd seen it fail for microscopic phenomena.
So they swung in the complete opposite direction.
Exactly. The electromagnetic worldview had three main components. First, a deep distrust of mechanical modeling, especially for what was happening inside an atom. Second, the fundamental belief that the only true physical realities were electromagnetic in nature, governed by Maxwell's equations.
And third,
A programmatic commitment to base all universal physics, molecular, thermal, everything, solely on electromagnetic laws.
so the goal wasn't to reduce everything to tiny billiard balls, but to reduce it all to field theory, to the dynamics of charge, current, and the ether.
That's it, precisely. Sommerfeld stated this explicitly around 1906. He argued that if Boltzmann successfully reduced thermodynamics to mechanics, then the job of the 20th century was to show that mechanics and thermodynamics must ultimately reduce to electrodynamics.
That's a huge philosophical commitment. It favors continuous fields over discrete mechanical concepts.
It does. And so, given this perspective, how could he possibly have accepted Planck's, and especially Einstein's, early quantum ideas, which suggested that energy and light were not continuous, but came in discrete packets?
He must have been highly resistant.
Extremely. Initially, he preferred Planck's approach because it seemed less radical. Planck introduced the quantum of action as a kind of mathematical fix for blackbody radiation, but he was hoping to reconcile it with Maxwell's continuous world.
But Einstein took it much more literally.
Einstein took the notion of the quantum of light, the photon deadly, seriously. He was saying light itself comes in discrete atoms. Sommerfeld, like many of his peers, felt that accepting this meant altering profoundly our fundamental conceptions of electromagnetic phenomena.
He was trying to save the continuity of Maxwell's equations within the atom, not just throw them out.
He was. And the sources point to a critical moment of tension and then eventual conversion around the 1909 Salzburg meeting.
Right. This is where he meets Einstein for the first time.
Yes, and Einstein was impressed. He called Sommerfeld a magnificent fellow. But the main debate there wasn't over relativity, which Sommerfeld was already working on mathematically. It was quantum theory.
And Sommerfeld was still skeptical of the light quantum.
He was clinging to the hope that some conservative extension of classical electromagnetism could fix the problems.
But that resistance just collapsed pretty quickly, didn't it? The following year, the evidence from his own students and a deep dive with Einstein in Zurich seemed to force his hand.
It did. After spending a week with Einstein in Zurich, Einstein wrote back to a colleague that Sommerfeld had made extensive concessions to his views, especially on quantum statistics.
And this shift wasn't purely philosophical.
Not at all. It was driven by the empirical failures of classical electrodynamics when you applied it to things like specific heat and radiation. And it was driven by the enthusiasm and the detailed work of his own students, like Peter Debye and Ludwig Hoff, who were getting results using these new quantum statistics.
This is a perfect example of the Sommerfeld school culture at work, isn't it? The commitment to mathematical and empirical truth just overrides the master's own philosophical preference.
It's the perfect example. His dedication to rigor, the very thing he honed in the engineering field, demanded that the successful mathematics had to prevail. So while he initially preferred the electromagnetic postulate, he quickly became the person to take the next incredibly messy step, formalizing Niels Bohr's atomic model.
So Sommerfeld makes this huge transition. He goes from trying to save classical electrodynamics to becoming one of the chief architects of the new quantum atom. And the groundwork had been laid by Niels Bohr in 1913 with this radical blueprint. Electrons exist only in discrete, stationary states, and light is only emitted during transitions between them.
That was the breakthrough, absolutely. But Bohr's model, while it was revolutionary, it was also conceptually crude and structurally very limited.
It really only worked for hydrogen, right, and it assumed these simple circular orbits.
Exactly. It couldn't explain the subtle splittings of spectral lines that experimentalists were seeing with high-resolution spectroscopy. This is where Sommerfeld's mathematical rigor became just indispensable.
So how did he generalize the model? What exactly did he and William Wilson add in 1915 with the Sommerfeld-Wilson quantization rules?
They moved the model beyond simple circles. For any multiply periodic classical system, Sommerfeld argued that you could apply quantization rules to each degree of freedom.
So for the atom, that meant allowing for elliptical orbits.
Precisely. And this required introducing additional quantum numbers to define the shape and the orientation of the electron's path.
This is a critical mathematical injection. So instead of just one number, n, for the size, now we need numbers to describe the geometry.
That's it. Sommerfeld's model needed two primary numbers: the radial quantum number, which governed how elongated the ellipse was, and the azimuthal quantum number, which governed the angular momentum and thus the shape.
And if the azimuthal number equals the principal number, you get a circle.
You get a circle. If it's smaller, you get an ellipse. The sources give a great visual for this. For n1, you only have one possibility, a circle. For n2, Sommerfeld showed you have a circle and one ellipse. For n3, a circle and two distinct ellipses.
So this immediately expanded the possibilities for electron orbits, which was exactly what was needed to account for the complexity they were seeing in the lab.
Yes, and here's the kicker. Because the electron is orbiting in an ellipse, its velocity changes along the path.
And due to relativity, that change in velocity means
It means the ellipse itself slowly precesses. It rotates in its plane. This tiny relativistic effect on the orbit's geometry was the key to unlocking the fine structure.
which brings us to the really massive achievement, the fine structure constant, alpha, which he introduced in 1916.
This constant, alpha, is one of the most fundamental numbers in physics. It's approximately 1 over 137.
A pure number. It determines the strength of the electromagnetic interaction.
That's the one. And Sommerfeld introduced it directly into his fine structure formula. This formula, which accounted for the splitting of spectral lines due to that relativistic precession of the elliptical orbits, it was a stunning success of the old quantum mechanics.
And its success was immediate and undeniable because it solved a major experimental puzzle with incredible accuracy.
It was crucial, especially when you compare it to the theoretical competition. Sommerfeld's prediction for those small splittings, the fine structure in the spectra of hydrogen and hydrogen-like systems like ionized helium, it agreed almost perfectly with the experimental data they had at the time.
And you mentioned a comparison to Schrödinger's early attempts. Can you elaborate on that? Why did Schrödinger, who would later become the genius of wave mechanics, get it wrong initially?
It's a fascinating historical note from the sources. When Erwin Schrödinger initially applied his own relativistic approach to the hydrogen atom, his calculated results for the fine structure splitting at the N2 energy level were off. They were off by a factor of 8/3 compared to Sommerfeld's results.
Which matched the observations.
Sommerfeld's mathematical treatment, even though it used the older quantum theory formalism, correctly handled the coupling between the electron's momentum and its energy in the relativistic framework. Schrödinger's early model just didn't account for the spin-orbit interaction correctly.
So Sommerfeld's empirical success solidified the old quantum theory as the best model they had right up until 1925.
It did. And this rigor was immediately codified into the book that defined a generation.
Tombow and Spectralinean, Atomic Structure and Spectral Lines, published in 1919.
It became instantly famous. Among physicists, it was known universally as the Bible of atomic theory.
What's remarkable about that book is how quickly it had to evolve just to keep pace with the revolution it was describing.
It was a living document of scientific chaos. The book went through 4 major editions just between 1919 and 1924. It was constantly being revised to incorporate groundbreaking results, like the discovery of electron spin or new spectroscopic data.
So it was the primary reference for that whole new generation, Heisenberg, Pauli, Fermi.
Absolutely. They all internalized the quantum principles from Sommerfeld's systematic, comprehensive text. It prepared them for the matrix mechanics and wave mechanics that were just around the corner.
And to manage that kind of rapid conceptual change, there had to be some kind of philosophical scaffolding that connected the new abstract world to the old known world.
And that was the correspondence principle. It was the vital conceptual bridge that stopped physics from becoming totally unmoored from reality.
Bohr interpreted it as the connection between quantum transitions and classical harmonics, right?
Essentially, yes. It stated that for very large quantum numbers, for electrons far from the nucleus, quantum physics has to smoothly merge back into classical physics.
And why was Sommerfeld's application of this principle so important?
Because it guided physicists to find the form of the new quantum laws. The sources emphasize a key point here. Both Bohr and Sommerfeld knew that the elliptical electron trajectories they were using were symbolic, not literal mechanical reality.
They knew the visualization was wrong at small scales?
They knew it failed, but the mathematics of those orbits defined the energy levels and helped them derive the rules. The correspondence principle provided the rational justification that allowed physicists to trust the new abstract quantum laws, even when they defied all classical intuition. It's how they transition from visualized paths to abstract quantum numbers. So if Sommerfeld's scientific contribution was injecting mathematical truth into the atom, his greatest impact on human history was, arguably, organizational and pedagogical. And this brings us right back to the Nobel paradox, because his true legacy is the generation of scientists he empowered, the unparalleled Sommerfeld School.
So how do we reconcile it? A man nominated 81 times who never won, with a man who mentored 8 eventual Nobel winners. Was the Nobel Committee biased against educators, or was he maybe just too willing to be the bridge rather than the final destination?
I think it was likely a combination of those things. He was seen by some as a synthesizer, not the ultimate revolutionary who came up with the final definitive theory. The glory went to Heisenberg and Schrödinger. And, the sources cite his own profound philosophy on this. He used to say, "Poor is the pupil who does not surpass his master."
Which suggests he was actively cultivating a culture where the goal was to surpass him.
Exactly. His success was measured by his students' ability to critically analyze and fundamentally improve upon his work.
That's a very unique measure of success in science. So what were the specific educational practices that created that environment, the one that produced such a dense concentration of genius?
Well, the structure was highly integrated and incredibly demanding. It went way beyond standard lectures. The core practices included formal lectures, specialized seminars where students would present advanced topics, the highly rigorous colloquium, and what they called out-of-class education.
Which was the vital informal setting.
The informal setting where the real creative discussion happened.
And the sources mention the famous Kaffee Klatsch tradition. This is where intellectual fellowship mixed with social life.
Exactly. And this wasn't just small talk. This was science operating in a high-intensity yet somehow relaxed social setting. T.S. Eliot, who was in Munich at the time, he immortalized this atmosphere in The Wasteland in 1922.
Write the line. We stopped in the colonnade and went on in sunlight into the Hofgarten and drank coffee and talked for an hour.
And the historical context suggests that while Eliot was observing his own group just yards away, Sommerfeld and his students were probably hammering out the latest conceptual hurdles in quantum physics over coffee. It was this constant intellectual grind, just disguised as social leisure.
That paints a picture of intense intellectual pressure, but also psychological safety. The sources distill this down to 4 key features of the school's culture.
Yes, and they're critical for understanding how quantum mechanics was born. First, there was open-mindedness based on pleasant relationships. Sommerfeld fostered collaboration, not intense rivalry. Second, they practiced challenging and specific problem-centered learning. This goes right back to his engineering roots. Physics was about solving concrete, difficult puzzles.
And third, a commitment to intellectual coherence.
Connecting classical theory, new math, and quantum ideas seamlessly. And the fourth feature.
The pursuit of social consensus based on criticism, that seems absolutely fundamental for a field that was having a revolution every 6 months.
It is the defining feature. In the 1920s, theories changed so fast. One year it's Bohr orbits, the next it's matrix mechanics, the next it's wave mechanics. To navigate that, the school implicitly emphasized the nature of science, the tentativeness of theories, hence the constant revision of his textbook, the empirical nature of the data, the creativity needed for solutions, and above all, the social dimension of science.
So ideas were tested, refined, and either accepted or thrown out based on community consensus, all driven by rigorous criticism.
Right, so Sommerfeld didn't just teach the theories. He taught the culture and the mechanism required to produce and validate new theories.
Which explains why his students were so successful at pioneering the next steps after him.
It's his ultimate legacy. He provided the environment, the mathematical tools, and the critical culture that allowed people like Heisenberg and Pauli to take the necessary radical leaps away from the Bohr-Sommerfeld model to establish modern quantum theory.
It is truly remarkable that even after the conceptual fireworks of the mid-1920s rendered the old quantum theory obsolete, Sommerfeld didn't just fade away, he pivoted. He applied the new quantum statistics he helped create to redefine a completely different field, solid-state physics.
This is a massive contribution that's often overlooked. His work in 1927, co-developing the free electron model, often called the Drude-Sommerfeld model, was the necessary bridge that connected quantum reality to the practical world of metals and electrical conductors.
Okay, so the classical Drude model had been around for a while. It treated electrons and metals like a classical gas. It worked okay for some things, like electrical conductivity, but it failed spectacularly on one critical measure: heat capacity.
It was a catastrophic failure, the heat capacity anomaly. According to the equipartition theorem of classical physics, every degree of freedom of a particle in a gas should contribute to the specific heat.
So the electrons in a metal, treated as a classical gas, should contribute a huge amount to the metal's heat capacity.
A very large amount, roughly 3/2 kBt per electron, where kb is Boltzmann's constant and T is temperature.
And when physicists actually measured the heat capacity of metals, what did they find?
They found almost no contribution from the electrons. The measured heat capacity of metals was almost exactly the same as insulators. It made no sense. Where was all that electron energy going?
So Sommerfeld's core innovation in 1927 was to apply the brand new quantum logic to this classical failure.
Precisely. He took the basic structure of the Drude model, a gas of charge carriers, and he combined it with the newly established quantum mechanical Fermi-Dirac statistics, which govern fermions like electrons.
And that was the key.
That was the key. Fermi-Dirac statistics incorporate the Pauli exclusion principle, which says no two electrons can occupy the same quantum state.
Okay, let's make this crystal clear. How does the Pauli principle actually fix the heat capacity problem?
So in the quantum model, at absolute zero, the electrons fill up all the lowest available energy states. They stack up like seats in a massive stadium, all the way up to a level called the Fermi energy. Now, to absorb heat, which is thermal energy, an electron has to jump to an empty state above it.
But because of the Pauli principle, almost all the electrons deep inside that stack have no empty states nearby to jump into. They're locked down.
They are completely locked down. So only a tiny fraction of electrons, the ones right at the very top of the stack, near the Fermi surface, can actually absorb that thermal energy and participate in thermal excitation.
That's the crucial insight.
It is. And it instantly resolved the anomaly. Sommerfeld's quantum model derived an electronic heat capacity, CV, that was proportional to temperature T, and showed it was roughly 100 times smaller than the classical prediction at room temperature.
Which perfectly matched experimental observation.
Perfectly. And it laid the foundation for modern band theory, which explains everything we know about solid-state materials today.
And beyond solving that one puzzle, the Drude-Sommerfeld model was incredibly successful at explaining other complex phenomena too.
Oh, it was a powerful, unified theoretical framework. It successfully explained the Wiedemann-Franz law, which released electrical and thermal conductivity in metals. It also gave quantitative explanations for electrical conductivity changes with temperature, the Seebeck effect, the thermoelectric effect, and thermal electron emission.
It was rigorous, successful, and showed Sommerfeld's skill in taking abstract quantum theory and grounding it in material reality.
And to get those quantitative results, especially for that temperature-dependent heat capacity, he needed some extremely sophisticated mathematics.
Which brings us back to his engineering rigor. He developed the Sommerfeld expansion.
He had to. To calculate quantities based on Fermi-Dirac statistics, you often end up with these really nasty integrals. The function you're integrating is multiplied by the Fermi function, which drops extremely sharply from 1 to 0 right around the Fermi energy.
And those sharp cutoff integrals are notoriously difficult to solve exactly.
They are. So the Sommerfeld expansion is an asymptotic expansion method specifically tailored for these Fermi function integrals. It lets you approximate the integral accurately at low temperatures, and you get these simple, closed-form expressions.
That's how he derived the famous result that the heat capacity is proportional to temperature.
That's exactly how. It just demonstrates that even his elite career work was characterized by him generating the required mathematical tools, just like he did with the gyroscope, to make sure his theoretical models yielded empirically verifiable numbers.
Now, moving from the hard physics back to the philosophical side, the sources also draw this deep connection between Sommerfeld's lifelong search for physical laws and ancient philosophy. He was described as being very much a Pythagorean.
And sometimes compared to Johannes Kepler, this speaks to his underlying intellectual drive, this belief in a deep mathematical harmony and proportion within the cosmos. He was searching for harmonic proportions, much like Kepler sought musical harmonies in planetary orbits. And modern research exploring this legacy finds some fascinating echoes of that.
Like connecting his fine structure constant alpha to geometry rooted in the golden ratio.
Exactly. And the connection seems to be more than just a numerical coincidence. One study cited in the sources noted a really compelling geometric relationship within the Bohr radius itself.
The Bohr radius, the size of the hydrogen atom.
Yes. They found that the Bohr radius is divided into two unique sections at the point of electrical neutrality, and this division adheres precisely to the golden point ratio. The golden ratio.
The golden ratio originating right in the structure of the atom. That's wild.
The study suggested that the golden ratio originates right in the core of atoms. It suggests that Sommerfeld's Pythagorean intuition about the universe having these geometrically beautiful proportions was perhaps a powerful, if philosophical, guide. His pursuit of elegance wasn't just aesthetic, it was functional. We really have to place Sommerfeld within the brutal political context of Germany from the First World War all the way through 1945. His leadership role during this period, it really transcended scientific theory. It became a crucial cultural and political bulwark against extremism.
And before the true political crisis hit Germany, Sommerfeld was actively cultivating his role as a global scientific figure. In 1928, for his 60th birthday, he undertakes this major 8-month world tour.
Yes, and that trip was strategically framed as a self-imposed cultural mission. He traveled across the Pacific to America, lecturing at major universities and scientific institutions. And he stated his mission explicitly. During a lecture in Tokyo, he said, "I am not merely a private individual and globetrotter, but an ambassador of German culture in the realm of science."
That's a remarkable statement. It shows his sense of duty to represent German intellectual excellence abroad, especially in what was a politically sensitive era.
It was. But that role as an ambassador of German culture was thrown into complete chaos when the nationalist movements, particularly the Nazis, sought to purge and redefine German physics.
And his resistance to this purification was lifelong.
It started very early. As far back as 1915, during the height of wartime nationalism, the physicist Johannes Stark, a prominent proponent of Deutsche Physik, or German physics, he labeled Sommerfeld the energetic executive secretary of the Jewish and fellow Semitic circle of theoretical physicists.
So Stark, who was deeply anti-Semitic, hated the abstract nature of quantum theory and relativity. He saw them as un-German.
He did. And he saw Sommerfeld as the organizational center protecting those ideas.
And once the Nazis consolidated power, that fight became a matter of preserving the integrity of science itself.
It became existential. Sommerfeld fought tirelessly against the efforts to purge the Jewish spirit from German physics. The most famous battle was over his own obligatory retirement in 1935. Sommerfeld and his faculty unanimously nominated Werner Heisenberg, his greatest student, to succeed him in the prestigious Munich chair.
And this choice was fiercely resisted by the proponents of Deutsche Physik.
Fiercely, led by Stark and Philipp Lenard, who were actively trying to suppress quantum mechanics and relativity as Jewish science.
This fight dragged on for years, with Sommerfeld risking his own standing to defend his student and theoretical physics itself.
He risked everything. He refused to bend to the political pressure and maintained his support for Heisenberg. And the level of personal attack escalated dramatically. In July 1937, an article in the SS magazine explicitly labeled Sommerfeld and Heisenberg, among others, as white Jews of science.
White Jews of science.
And agents of Judaism in German intellectual life who needed to disappear just like the Jews themselves.
That is just venomous, terrifying language from the highest ranks of the regime. The fact that he continued to fight in that climate shows immense moral courage.
It does. And the political climate ultimately shattered any national feeling he once had. By 1933, after just 15 months of Hitler's rule, Sommerfeld noted this profound personal shift. He wrote that the misuse of the word national by the Nazi rulers had thoroughly broken him of his former national feeling.
And he expressed a willingness to see Germany disappear as a power and merge into a pacified Europe.
It's a shocking statement. His devotion shifted entirely from nation to the abstract truth of science.
And despite these turbulent times, and the fact that the Heisenberg succession fight was ultimately lost, at least initially.
It was. A Nazi Party member was installed for a time.
Despite all that, Sommerfeld's scientific influence remained profound right until his death.
It did. Arnold Sommerfeld died tragically on April 26, 1951, in Munich. The sources state he succumbed to injuries from a traffic accident while he was walking with his grandchildren.
But his legacy was immediately secured by the very students he mentored.
Absolutely. His textbooks were lovingly revised and republished by his students, ensuring his rigorous methodology remains central to physics education globally. And fittingly, his life's work continues to be recognized. In 2004, the Center for Theoretical Physics at the University of Munich, the place where he educated so many giants, was officially named the Arnold Sommerfeld Center for Theoretical Physics.
So the recognition arrived, even if the Nobel did not. #tag outro. What a monumental, multifaceted career. I mean, defined by mathematical precision on one hand and moral courage on the other. When you look at the whole sweep of his life, Arnold Sommerfeld emerges not just as a great physicist, but as the indispensable bridge builder of modern science.
He really was the connector. He took his rigorous background in applied mechanics and mathematics, which he honed on things like gyroscopes and bridge vibrations.
And applied that exact same mathematical commitment to the highly abstract theoretical atom.
And he took Bohr's initial conceptually limited idea and he quantified it, most notably with those relativistic corrections that led directly to the fine structure constant.
He achieved empirical agreement where others who were relying on less rigorous math initially failed.
He did. And then he corrected the flawed foundations of classical solid-state physics using Fermi-Dirac statistics, resolving the heat capacity anomaly and laying the groundwork for everything we now know about semiconductors and modern electronics.
He navigated this dizzying transition from the mechanical worldview to the electromagnetic worldview, and finally into the quantum worldview, not by abandoning his principles of rigor, but by applying them relentlessly.
He was truly the ultimate facilitator of the quantum revolution, the master teacher who made sure that the revolutionary ideas were mathematically sound.
And that leads us to the final provocative thought we want to leave you with, connecting his engineering roots to his abstract achievements.
We noted that Sommerfeld's successful early quantum work, like Bohr's, required him to treat the electron trajectory in stationary states as symbolic. They weren't literal visualizable paths. So given his profound professional roots in applied physics in dealing with tangible, measurable, and visualizable things like hydrodynamics, lubrication, and bridge dynamics, how did that deep, practical, real-world experience ultimately allow him to become one of the greatest guides into the purely abstract world of quantum theory?
It suggests that maybe the greatest theoretical leaps, those into the truly bizarre and counterintuitive realms of physics, don't necessarily come from those who start in abstraction, but from those who possess the strongest, most grounded, most rigorously tested mathematical tools. Tools that are capable of ensuring that even abstract concepts adhere to measurable, verifiable reality.
The engineer provided the toolkit for the philosopher to succeed.
A profound thought for any learner to consider as they approach a new, complex field.